In this video, we're going to talk about quadratic functions and some applications of quadratic functions. We're going to learn how to graph these types of functions, different forms for them, and how to use them in word problems. So let's start with a definition of what a quadratic function is. A function defined by f of x equals ax squared plus bx plus c is a quadratic function. And we should note that a has to be not equal to 0. So it's very important to have that x squared term when we're talking about a quadratic function. Now, these quadratic functions can be written in a different form that makes them really nice for graphing, and that form is called vertex form. To get a quadratic function into vertex form, you actually get to complete the square, like what we learned in the last video for how to solve a quadratic equation. So by completing the square, f of x can be expressed in vertex form. Which is f of x equals a times x minus h in parentheses squared plus k. Now, the reason that this is called vertex form is because the vertex of your parabola, the point that's either at the very top or at the very bottom, is actually given by h comma k. So you can look at this form of the parabola and actually find the vertex without doing any work. Now, when you're graphing one of these functions, you know you're going to get a parabola. And the parabola is going to open upward if a is bigger than 0 and open downward if a is less than 0. So our parabola opens up if a is bigger than 0. And it opens down if a is less than 0. That vertex is going to be either your maximum or your minimum of the function. And it depends on whether it's opening up or down. If your parabola happens to open up, you have a minimum value at your vertex. And if it opens down, you get a maximum at your vertex. You can see that just by looking at pictures. Your axis of symmetry is the vertical line x equals h. This is just the vertical line that goes through your vertex. So if this were my vertex here, hk, this is x equals h, the axis of symmetry. It's just a vertical line that goes directly through your vertex, and your graph is going to look the same on both sides of that line. So let's do an example. We're going to do a lot of different things with one function here. So for the function g of x equals x plus 2 squared minus 1, first thing we're going to do is determine if the graph opens up or down. Now remember, we can tell if it opens up or down by looking at the a value. And in vertex form, your A is the number multiplied in front of these parentheses. So in this particular problem, my A would be a 1. I don't have the 1 written there, but we all know we're multiplying by 1. So A is equal to 1, which is bigger than 0. So since it's positive, this means it opens up. Part B, identify the vertex, X-intercepts, and the Y-intercept. Well, the vertex we should be able to get by just looking directly at this equation because it's in vertex form. Your vertex is supposed to be the point HK. Now, I have found that students sometimes struggle finding what the H value is, but they're usually good at the K value. Remember that the vertex form was A times X minus H squared plus K. So your K is the number on the outside, -1, but your H is the opposite of the number that's on the inside. So since it was a minus H in the parentheses and I have a positive 2, I know my H is actually -2. So my vertex is the point -2, -1. To find my X-intercepts, we do exactly what we did in earlier sections. We have to find when the function is equal to 0. So I want to solve when my entire function is equal to 0. And we know how to solve something like this because we know how to solve quadratic equations. First thing I'm going to do is add 1 to the other side. And I'm going to use that square root property to solve this. X plus 2 is equal to plus or minus the square root of 1, which means X plus 2 is plus or minus 1. So I have two possibilities, X plus 2 equals 1 or X plus 2 equals -1. If X plus 2 is equal to 1, I get X is equal to -1. And if I get X plus 2 is -1, I get X equals -3. So my X-intercepts are the points -1, 0 and -3, 0. And now to find the Y-intercept, I know the Y-intercept occurs when my X is equal to 0. So for the Y-intercept, we have to plug a 0 into our original function. 0 plus 2 is 2, square it to get 4, subtract 1 to get 3. So my Y-intercept is the point 0, 3. Now, part C, we're going to graph, well, actually just sketch what this looks like. So part C, sketch. Now, when it says sketch, it doesn't have to be an absolutely perfect graph. You can get a pretty decent graph just by plotting your vertex, your X-intercepts, your Y-intercepts, and remembering which way the parabola opens. So if I put all those points on there, we found that our vertex was at -2, -1. That's right here. I had X-intercepts of -1, 0 and -3, 0. And I had a Y-intercept at 0, 3. And you can already see part of this parabola shape. Our parabola is supposed to be opening up, and this is opening up. So when you're sketching, just get a few points on there and connect it with a fairly smooth curve, and there's the sketch of our parabola. Now, part D, what is the axis of symmetry. Now remember, your axis of symmetry is the vertical line that passes through your vertex. It's x equals h. So in this particular problem, x equals -2. My axis of symmetry, I'm just going to put it in green on my graph so we see it, is that vertical line, x equals -2. Part E, what is the minimum or maximum value for this function? Well, we can see by our graph that we have a minimum value. There's a point that's the lowest point on the graph. So I have a minimum value, and the value is going to be the y. So that is a minimum value of -1. It occurs at x equals -2, but the actual value is -1. Last thing, domain and range. The domain, you can see from our graph, we can plug in any x values we want. It's going to go on forever. So my domain is -∞ to +∞. But my range is not all real numbers because I don't hit any of these y values below my vertex. So my smallest y value is -1, but I continue up forever. So I get a range of -1 to infinity. All right, so that's a lot of things in one problem, but it shows you how you can do a lot of different things just given the equation in vertex form. Vertex form makes it super easy to graph, but what if you're not in vertex form? Can we convert an equation to vertex form to make it easier to graph? Yes, we can, because we know how to complete the square. So to write f of x equals ax squared plus bx plus c in vertex form, we just have to complete the square. And we're going to follow the same exact steps we used to complete the square when we learned how to do it to solve quadratic equations. We just don't have to solve afterwards. Once it's written all factored, you're good to go. So let's do an example where we do that. I am going to warn you, it is a little strange putting it in vertex form. It's going to look a little bit different than our completing the square before, because when we completed the square in our last video, we only had a number on one side of the equation. Now we're going to have something involving a function name, f of x. So let's write f of x equals 3x squared minus 6x plus 1 in vertex form. Now remember, from our last video, the first thing you have to do to complete the square is divide everything by a. My a value in this problem is 3. So the first thing I'm going to do is divide everything by 3. So I get f of x over 3 equals x squared minus 2x plus 1/3. Don't be concerned about this f of x over 3. It's okay. It's all going to just fix itself in the end. So you're just going to have to get used to ugly notation to get through the procedure, but it will all work out in the end. The next step in completing the square is to isolate the terms that have our variable. So I need to move this 1/3 over to the other side. When I move that 1/3 over, I'm going to get f of x over 3 minus 1/3 equals x squared minus 2x. And now's the part where we do the completing the square step. Remember, we have to add our b over 2 squared to both sides of the equation. in this particular problem, the b that I'm working with now is -2. So I need to add my -2/2 squared to both sides of the equation. Now let's see what we get. I have f of x over 3. What is -2/2 in parentheses squared? Well, -2/2 is -1. When you square it, you get 1. So I have a -1/3 and a +1. And on this side, x squared minus 2x plus 1. We know the next step is to factor. So I'm going to factor this right side. And remember from last time, you're going to get x plus or minus something squared. And it's always going to be your b over 2 that goes in there. So I have -1. X minus 1 in parentheses squared. On this left side, I still have f of x over 3. -1/3 plus 1 is +2/3. Now, this still isn't quite vertex form, but it's super close. To get it completely in vertex form, now I just have to get f of x by itself again. So let's subtract 2/3, back over to the other side. And to get f of x completely by itself, we have to multiply everything by 3. And so when I multiply everything by 3, I get f of x equals 3 times x minus 1 in parentheses squared minus 2. And now we have vertex form. So that completing the squared procedure from last time does come in handy because it allows us to write this in vertex form, which then makes it very easy to see the vertex and to graph the graph of the function. Now, what if you're asked what the vertex is and they don't actually want you to put it into vertex form? Well, luckily, there's a formula to find the vertex as well. So for f of x equals ax squared plus bx plus c, the vertex is given by the x-coordinate is -b over 2a, and the y-coordinate is whatever you get when you plug that x value into your function. So, for example, what is the vertex of f of x equals -x squared minus 4x minus 7? And then sketch the graph using the vertex, X-intercepts, and Y-intercept. So first we'll find the vertex. The x-coordinate of my vertex is -b over 2a. So for this particular problem, -b would be +4, and 2 times a is 2 times -1. 4 over -2 is equal to -2. So the x-coordinate of my vertex is -2. To find the y-coordinate, we just have to plug that -2 into my function. F of -2 equals -2 squared minus 4 times -2 minus 7. And then I just have to simplify that. Well, negative 2 squared is positive 4. So the opposite of that is negative 4. Negative 4 times negative 2 is positive 8. And I have a minus 7. So this ends up being negative 3. So my vertex is the point negative 2, negative 3. Now to complete this problem, we still need to find our x-intercepts and our y-intercepts so that we can graph this. Let's start with, I guess we'll do the x-intercepts first. For your x-intercepts, remember, that is where your entire function, which was negative x squared minus 4x minus 7, where that is equal to 0. So just for fun, I'm going to use the quadratic formula this time to solve it. Using my quadratic formula, x is equal to the opposite of b, so that's 4, plus or minus the square root of my b squared minus 4ac, all divided by 2a. And I just have to simplify this to find any x-intercepts. And I get that x is equal to 4 plus or minus the square root of 16 minus 28 all over negative 2. Now I want to point out, underneath that square root, we're going to have a negative number. And although we do know how to calculate the square root of a negative number, our x-intercepts are always real values for x. So this is no real solutions. So that means there are no x-intercepts. That's okay. It's possible to not have x-intercepts. Perhaps our parabola opens up and it's above the x-axis. Or actually, in this case, it opens down, but it's below the x-axis, so it never touches it. Now to find our y-intercept, remember our y-intercept is just what happens when we plug a 0 into our function. So I get negative 0 squared minus 4 times 0 minus 7, which is negative 7. So my y-intercept is the point 0, negative 7. So if I'm going to sketch this using just my intercepts and that vertex, you might think that's not enough information, but it's enough to get a sketch. Okay, so my vertex was the point negative 2, negative 3. So I'm going to put my vertex on here, negative 2, negative 3. There's my vertex. And my y-intercept was 0, negative 7. I know my parabola opens down, and I know that it's going to be symmetric across my axis of symmetry, which goes through my vertex. So that means since I have a point over here at negative 7, there's going to be a mirror image of that over here. Notice that when you look at the difference between the x values, this point is 2 away from this point, just in the x values. So that means on the other side of my axis of symmetry, I have to be 2 to the left of that, and down here at negative 7. That's the mirror image of that guy. And then I can connect those 3 points and get a sketch of the function. All right. So just a note for us, even though we kind of discovered it in the problem we just did, your x-intercepts are the real solutions to f of x equals ax squared plus bx plus c set equal to 0. But it's only the real solutions. But we know something about solutions of quadratic equations. We learned about the discriminant in our last video. If b squared minus 4ac is positive, we know that that means we have two real solutions. So that means we're going to have two x-intercepts. If b squared minus 4ac equals 0, that was one real solution. That means one x-intercept. And if b squared minus 4ac is negative, from our last video, that meant that we had two non-real solutions. But since we only have real solutions as x-intercepts, this means we have 0 x-intercepts because all of my solutions were non-real in this case. All right, so what we have left for this video is just some application problems. That, of course, means word problems, and we're going to do 2 of them. So for our first word problem, a quarterback throws a football and the height of the football can be modeled by the function h of t equals negative 16 t squared plus 30.4 t plus 5, where h of t is height in feet and t is time in seconds after release. So it's the amount of time after the ball has been thrown. So notice that this model for our football path makes a parabola. We have a quadratic curve representing the height of this football. The first thing we're going to answer with this problem is at what time is the ball at maximum height? So at what time is the ball at maximum height? Well, let's think for a second. We know that with all parabolas, we have either a minimum point or a maximum point. We have a maximum point when the parabola opens downwards, which means that our A is negative. Our A is negative in this problem, so we do indeed have a maximum point. Where does that maximum occur? At the vertex. So to find the vertex, I know that it's going to occur at t equals negative b over 2a using my vertex formula. So I just have to plug in my b and my a into that formula, and it will tell me when we reach the vertex, which is where the ball is highest. So for this particular problem, my b was 30.4. So I get negative 30.4 over 2 times my a, which was negative 16. And that, when you simplify, is 0.95 seconds. So the ball reaches its maximum height at 0.95 seconds, and that's when it starts coming back down. For part B, What is the maximum height? Well, that's asking for the other coordinate of our vertex. So all we have to do is plug this t value into our function. H of 0.95 will get me the height of the football. So I get negative 16 times 0.95 squared plus 30.4 times 0.95 plus 5. And when I simplify that, that will get me the maximum height of the ball. This is negative 16 times 0.9025 plus 28.88 and plus 5. And we have, multiplying these two together, negative 14.44 plus 28.88 plus 5. And when I add all of that together, I get 19.44 feet. So at its maximum height, the football was 19.44 feet above the ground. Last part for this problem, part C. How long does it take for the ball to reach the receiver if it is caught 3 feet off the ground? So notice this is asking us how long it takes. That means we're going to have to solve for t, our time. This means that that 3 feet where the ball is caught, that's what we have to set our function equal to. We're trying to figure out the t value. So we have to solve negative 16t squared plus 30.4t plus 5 equals 3. And if I solve this, that will tell me the time where this receiver caught the ball. First thing I'm going to do is move this 3 over to the other side, so we have a quadratic equation set equal to 0. And now we would just have to decide how to solve this. I personally would use the quadratic formula on this particular problem. So we want to solve this using our quadratic formula. T equals the negative b plus or minus square root of our b squared minus 4 times our a times our c all over 2 times our a. So I just used my quadratic formula with a equals negative 16, b equals 30.4, and c equals 2. When I simplify this, I have negative 30.4 plus or minus when you do the 30.4 squared and then minus 4 times negative 16 times 2, you're going to get a square root of 1052.16. And all of this is over negative 32. So we have 2 possible solutions. One of them is the solution that uses a plus. Negative 30.4 plus a square root of 1052.16 all over negative 32. But if you type that in, you're going to get It's approximately negative 0.06 seconds. And this is not an appropriate solution to this problem because we can't have negative time. This means that the receiver would have caught the ball negative 0.06 seconds before the quarterback even threw it. That doesn't make any sense. So this solution is not the answer, and we get to throw it out. So let's try the other possibility. The other possibility for a solution is the one that uses a minus in it. So t equals negative 30.4 minus the square root of 1052.16 all over negative 32. And when you type that one into your calculator, you'll get t is approximately 1.96 seconds. And that makes more sense. This means that the quarterback throws the ball and the receiver catches it almost 2 seconds after it's thrown, 1.96 seconds. All right, so when you're using quadratic functions in a word problem, you always need to make sure you think about what the problem means. Because sometimes, like we just had, you get a solution that doesn't actually make sense. It doesn't make sense to have negative time in that problem. So we knew that that possible answer was incorrect, and it had to be the other answer. Let's finish up with one last word problem. We have a farmer who has 200 feet of fencing and wants to build 3 adjacent rectangular corrals. Determine the dimensions that maximize the area and find the area of each corral. All right, and I'm going to draw the picture that came with this problem so that we can help set it up using our picture. So we have 3 adjacent rectangular corrals, and that just means we have 3 rectangles sitting directly next to each other, and they're all exactly the same size. So we have X, 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 and X. And the distance all along the bottom is going to be y. So that's our situation there. We want the maximum area. Well, the problem is that just knowing the area, well, the area of this whole thing is x times y. But how do I make that as big as possible? I need to use everything in my problem. In particular, I need to use this 200 feet of fence. That 200 feet is referring to the amount of fence that makes all of these sides all added up. So let's first write an equation for the amount of fence. What we know is that all of the sides added up should equal our 200 feet of fence. If I look at all my vertical sides, I have x, 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 and x. So that's 4x. And I have the bottom and the top, both of those are y. 4x plus 2y is going to equal my 200 feet of fencing. And I know my area is x times y. That's the area for the whole corral without counting each individual one. So I want this to be as big as possible, but I have 2 variables there, and that makes it a little hard. So what we're going to do is take the other equation and solve for one of our variables. This is a system of equations. So I'm going to take my top equation and solve it for y. I get 2y equals 200 minus 4x. And when I divide by 2, y is 100 minus 2x. Now, why did I do that? Well, because now I can look at my area, which was x times y, and I can replace the y with 100 minus 2x. This means that my area, if I distribute that x value, my area is equal to a negative 2x squared and a positive 100x. And we have a quadratic function here. That's important because we know how to find the maximum or minimum of a quadratic function. It's going to be our vertex. Notice that this particular quadratic function is opening downward, so it does have a maximum, so that's good. Our max is going to be at the vertex. So I have x equals my negative b over 2a. Negative 100 over negative 4 is positive 25 feet. And for my y value, remember that our y was equal to 100 minus 2x. So this means I have 100 minus 2 times 25, and my y is then equal to 50 feet. Those are the dimensions that give me the biggest area. So we find the vertex using our negative b over 2a, and then you can find the y value by plugging the x value into the expression we had for y. So my dimensions were 25 feet by 50 feet. The last thing they wanted me to calculate was the area of an individual corral. So remember what the picture looked like. We had x, 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 and y all across the bottom. The area of an individual corral, so just one of the 3 rectangles, I have an x for one side times, it would be 1/3 of y. Because y is all the way across and it's been divided into 3 separate corrals. So then I just have to plug in the values I found. X was 25, y is 50, and when I plug all of that in, I get 1,250 over 3 square feet, which if I put that in decimal form, is about 416.7 square feet. That's the maximum area for one of these corrals. All right, so that's all I have for you today. I hope you enjoyed the word problems in particular. And in our next video, we're going to learn about some other types of polynomial equations and functions, not just quadratics. So if you have any questions, feel free to drop them below. If you're a current student, you can also ask in email or through office hours, and I'd be happy to help. I'll see you in the next video.